In this lecture, we will be introducing the concept of ARIMA processes, or autoregressive integrated moving average processes. First, let's recall our definition for an ARMA process, or an autoregressive moving average, order PQ process. So the idea behind such a process was to combine pth order autoregressive processes and qth order moving average processes to create a robust class of models to model stationary time series. And here was our definition. We have our white noise process of epsilons, and we say y1, y2, y3 is an ARMA PQ if, for parameters mu, phi1 through phi p, and theta1 through theta q, we have the following defining equation. And so we can work on any time scale, but if we think of t on a daily time scale, we can interpret this as the way yt differs from its mean today is it remembers a piece of how it differed from its mean yesterday, plus a piece of how it differs from its means 2 days ago, down to how it differed from its mean p days ago. We have a new noise term representing new information, the effective new information, and then we have q of these memory terms for the past noise terms. So we have a piece of the noise term from 1 day ago down to a piece of the noise term from q days ago. And with certain conditions on these parameters, the phis and the thetas, we have to look for something called a unit root, which we would look at in a separate lecture. We can have conditions for stationarity of such a time series. The issue becomes we have a nice robust model for stationary time series. And keep in mind that allowing memory p days in the past for previous values of itself and q days in the past for previous values of the noise terms gives a lot of different possibilities for dependence, autocorrelation. So this kind of auto-dependent structure that you can have with y and previous values of itself. The issue is, in real life, many time series that we encounter are in fact non-stationary, or at least exhibit evidence of non-stationarity. Can we use ARMA models when we have time series that are not stationary? The answer is yes. But first, let's just take a look at an example of a non-stationary process, and one that we've already looked at. And so, random walk. Suppose we have our white noise, so a strong white noise process, meaning that these epsilons are independent. In particular, they're normal. And let's define our random walk in this way. So we have a starting value x naught, and then for natural numbers t, so time 1, 2, 3, 4, 5, we define our random walk as the initial value plus the summation of the white noise terms up to time t. So you can think of this gives us x1 is x naught plus epsilon 1, right? We would have the sum n equals 1 to 1. x2 is x naught plus epsilon 1 plus epsilon 2. So we call it a random walk, and you can see here the idea is that at each time we take a new step, which is, in this case, normally just mean zero, constant variance distributed. So we tend to think of a random walk so if this is our xt axis, imagine someone walking, if we're looking at a bird's eye view on this, and the person starts out here, say at x0, say that's equal to 0, and we're seeing footprints in the snow as the person is stumbling to the right. So maybe the first epsilon at 1 is positive, and maybe the second one is largely negative. And the idea is that we're getting these things that look like these kind of random footsteps. Now, let's recall that for a process to be stationary in the weakest sense, weak stationarity required a fixed mean and a fixed variance. So let's take a look. In this case, our mean would be the expectation of that defining equation, right? X naught plus the sum of the epsilon n's. And by linearity of expectation, this becomes the expectation of x naught plus the sum, n goes from 1 to t, of the expectation of the epsilon n's. And we know that each epsilon n is mean 0. X naught is a constant, so this turns out to be x naught. So no issue there. We do have a fixed mean. But what about the variance? So the variance of xt will be the variance of x naught plus the sum n equals 1 to t of epsilon n. Now the key thing here is that, number one, x naught is a constant, and number two, these epsilon n's are independent. And by independence, this means the variance of that sum will be the sum of the variances. So this is a constant. It just represents a translation. It does not have an effect on the variance. We can show that directly from the definition if you like. But the result of that will be the same variance as just the sum of the white noise terms. And now, because they are independent, the variance of the sum will be the sum of the variances. And it's critical to note here that this is because the epsilon 1 to epsilon n are independent. Because of that, we can take this step. If you didn't have this step, you would have covariance terms appearing. But we also know from our white noise distribution, the white noise terms, the epsilon n's, all have this variance sigma square. So this is sigma epsilon square. And so we're adding up t copies of the same constant, and so this is equal to t times epsilon, sigma epsilon square. And this is not constant. So this depends on t, which means our random walk is non-stationary. We would to have the weakest form of stationarity, we would need both a fixed mean and a fixed variance, and we have a time-dependent variance. Okay, pretty standard type of process, random walk, but all hope is not lost. We still may be able to do something with a non-stationary process with stationary modeling, and the idea is, let's take our first difference. So let's recall our backwards operator b and our difference operator delta. And the idea here is, if we distribute this operation, this is xt minus bxt, and the idea of the difference operator is that the difference operator is using this backwards operator, and the backwards operator backs up that process 1 unit in time. So by differencing, we may be able to see something useful in terms of the original non-stationary process here, this random walk. So our delta xt, let's use our definition. So we have xt So we have x naught plus the sum, n equals 1 to t of epsilon n. So there's our xt. Then we subtract xt minus 1, which is the same expression, except the upper limit of summation instead of t is t minus 1. And you know you can pop off one term in here. So we can rewrite this as x naught plus the sum. Let's just pop off the top term. So we'll sum n equals 1 to t minus 1 of epsilon n, and then we still have that epsilon t, minus x naught plus the sum n equals 1 to t minus 1 epsilon n. And we now see that the x naughts cancel and the sums cancel, and what remains is just this epsilon t term. So the delta xt is epsilon t. That is, right, delta xt is epsilon t. That's our white noise process, which by definition we know is stationary. So this was worth, the reason we went through this is to note that we started with a non-stationary stochastic process, and we took its derivative, or its first difference, and the result was a stationary process. And this is key for use of models like the ARMA model in the modeling of non-stationary processes via differencing. So many time series are non-stationary. It's very common in practice when you take time series data that you have non-stationarity. But we can simply difference them or take their derivatives. And a general heuristic rule, if a time series is non-stationary, usually its first or its second order differences are stationary. So we can start off with an original time series. We can take its first difference, as we have here, or its second difference. So if we take the difference again, we can think of this delta squared x as delta times, or delta operating on delta x. Here is our delta x. So when we do our difference operator, remember the difference operator is 1 minus the backward operator. Here this becomes, we distribute the 1, so we have xt minus 1. And then we do the b. So we have minus bxt minus a minus, so plus bxt minus 1. And recall what the backward operator does. So this is xt minus xt minus 1. This b backs up this xt 1 unit, and so we'll get minus xt minus 1. And this b backs up the xt minus 1 unit, so plus xt minus 2. And we see two of these are the same, and the result is xt minus 2xt minus 1 plus xt minus 2. And so what we typically see in practice is that if our original time series is not stationary, we can take its derivative, its first difference, and we look for stationarity there. If we don't get stationarity there, we can do a second difference, and we will usually see stationarity there. In theory, you can continue third difference, fourth difference, but generally it's 1 or 2 differences to achieve stationarity. Once we have a time series after differencing that is stationary, we can then model that stationary time series using an ARMA model, which gives us the definition of the ARIMA model, or the ARIMA process. And so ARIMA really is an ARMA model with an I there and its own parameter D. So this I and this D are linked, and we're saying it's an autoregressive integrated moving average process. And the idea is you need to difference your original time series D times to get something that is stationary, which is then modeled as an ARMA PQ. And that's what we call an ARIMA PDQ process. So in the case of our example with the random walk, we would say that's an ARIMA, actually would be ARIMA 010 process. Now, it's important to note that you want to difference YD minimally, because there is danger in over-differencing. You can add in some strange correlation structure that you don't want, autocorrelation structure you don't want if you difference too many times. So you want to think of this D as the minimal number of times that you need to difference your original YT in order to achieve a stationary process. So once you do that, you can model your difference process, your D times difference process, call it XT. So XT will be ARMA PQ. But then recall that the inverse of differencing or differentiating a time series is integrating a time series. So you can then integrate that ARMA model D times, and you now have a model for your original non-stationary time series YT. And that's the real power of the ARIMA model. When you first study ARMA models, it feels restrictive because you're working with a class of models that works very well for stationary time series. But then when you realize that you can take a non-stationary time series, take its derivative D times to achieve a stationary time series, model that stationary time series as an ARMA PQ, and then integrate your model D times, undoing that differentiation, and you have a model for your non-stationary time series. This gives us an incredibly robust class of models for non-stationary time series. The natural question to then ask, how do you choose P, D, and Q? And so that would be an issue of model calibration, which we will get into in the next lecture.